All right, so barium ion, this is a part on barium ion. 2 plus. And so it would lose 1 electron goes to 55, 2 electrons is going to go to 54. So what's isoelectronic with 54 electrons? It would be xenon. And so barium 2 plus has the electron configuration is xenon. And so what we need is we need 2 other ions with the xenon configuration. Well, one of them would be cesium plus. Cesium plus would have 54 electrons as well. The other ones you could name would be like iodide. Iodide would be I minus, so it has an extra electron, which would bump it up to 54. Or telluride. Telluride would be Te2 minus, so it would go 52, 53, 54 electrons. So anything with 54 electrons would be isoelectronic with barium 2 plus. Barium 2 plus is isoelectronic with xenon. Therefore, anything with the xenon configuration is okay. Does that answer?
Yeah, so it would be iodine because it's close enough to xenon, or is it less than 4?
Well, anything that is going to go, not just iodide, iodine, but tellurium, antimony. Antimony would be sp3 minus, and that would form antinomide. So anything that's going to go to xenon. It's like basically anything in that shell will want to either gain or lose electrons to be, well, if it loses, it's going to go to krypton, or in this shell. So rubidium and strontium, those would go to krypton. So rubidium and strontium wouldn't gain, go to xenon. So this would be too many. And so anything close to xenon is going to an ion that's going to be isoelectronic. That's usually, for the target. We looked at neon, and so carbide, nitride, oxide, fluoride are all isoelectronic with neon. And then sodium plus, magnesium plus, aluminum 3 plus are all isoelectronic with neon. So anything within that range of neon is isoelectronic. Does that make sense? Yeah. All right, other questions? What do I mean by what?
Hybrid.
Hybrid? Resonance hybrid?
Yeah, well, it says draw the hybrid.
Okay, I'll talk about that. I haven't talked about it. I'll talk about it. Other questions? Well, there's a quantum homework in the supplement too. I just want the quantum. You don't have to do the periodic table. Was that a periodic table question from the homework? Quantum. Was that from the book or was that from the supplement? It's from the book. So this test is going to have, chapter 8 and 9 type material, but only redox reactions, as we mentioned the other day. Chapter 19 has some redox there. The reason I didn't talk about chapter 19 now is because it also includes batteries, which I don't want to get into now. But when you have redox reactions, what method do you use? Like if you have a redox reaction like this, what method do you use? Well, someone just remind me what the methods are for solving redox reactions. You have it? Or just a method?
Chart method?
Chart method. chart method's probably the number one method. Chart method, skeleton, redox, single replacement, and well, half reactions would be the chart method. That's what I call the chart method. And combustion. Well, what method would you use here? Well, what we do is we just try the chart method. Chart method is the number one method. And so chart method, we inventory and then see are the species on the chart. You know, is bromine on the chart? Yes. Is iodide on the chart? Yes. So we just copy down the half reactions and add them up. That's all we do, and figure out if there's a driving force. So the chart method, the species are on the chart. And so we can figure out what they're doing. Water, you know, water would be the other item. These are simplified because there could be other species in the inventory, but you know, here they're trying to make it a little bit simpler. So they're telling you the reactions between nickel 2 and cadmium. And so we look, is nickel 2 on the chart? Nickel 2 is on the chart in this book. It's not on the chart I gave you on the handout, nor is cadmium, but you know, those would have to be on the chart, probably. But or you can figure it out. H plus is on the chart, bromine's on the chart, chlorine's on the chart, iron's on the chart. How about NO and water and iron? Are those on the chart? Iron too? Yes, all those are on the chart. And so we could use the chart method to write out the half reactions and then just figure out, you know, based on what the strongest oxidizer and the strongest reducer are. H plus and magnesium, those are on the chart. Water. But we had other reactions which were not on the chart. For example, this is thiosulfate. Is thiosulfate on the chart? No, thiosulfate's not on the chart. Is chlorine on the chart? Yeah, chlorine going to chloride's on the chart. You know, we could just copy it from the chart. The half reaction would be chlorine plus 2 electrons yields chloride. But what about this one, thiosulfate going to sulfate? Well, that's not on the chart, so how are we going to figure out the half reaction for thiosulfate goes to sulfate? We use the skeleton redox method. Now, the skeleton redox method, we balance, they didn't go through it here, they skipped some steps. But this one we just copy off the chart. You know, chlorine plus 2 electrons goes to 2 chlorides, and then they doubled it because they want 8 electrons instead, or actually quadrupled it. They want 8 electrons. But here, thiosulfate goes to sulfate. First, you balance all elements other than oxygen and hydrogen. So two sulfurs here, 1 sulfur here, so change the coefficient to 2. Then you balance out the oxygens. 3 oxygens here, 4 oxygens here. Actually, no, 8 oxygens. 3 oxygens here, 8 oxygens here. We need 5 oxygens, so add 5 waters. Then we balance out the hydrogens. 10 hydrogens here, no hydrogens here. We add 10 H plus. Then we balance out the charge. You know, minus 2 plus 0 is minus 2, and then minus 4 plus 10 is plus 6. So plus 6 minus 8 gives us minus 2, so the charge is down. And then we add up these, and then in this case, for this one, how did they know thiosulfate goes to sulfate? How they knew that is they just mixed it together to see what happened. You know, this is often the case in redox. This is often the case because you know, how do you know like carbon monoxide is going to form? Did I talk about the carbon monoxide deaths this past weekend? The carbon monoxide deaths? Yeah. No? Did I talk about that? Yeah, over the weekend there are a number of deaths from carbon monoxide poisoning. Well, carbon monoxide is a very insidious poison because you can't smell it. well, just over the weekend, I mean, every weekend there's carbon monoxide poisoning deaths, but you can't smell. Carbon monoxide has some interesting properties to make it. What does this say? This said something like there were 56,000 deaths in a 10-year period. $56,133 deaths from 1979 to 1988. It's a lot. But, you know, this was just in the news. Let's see. This was just in the news because, you know, there's so many. Family of 4 and their 3 dogs were found dead in their home. Carbon monoxide. Couple found in a tent 9 days ago. Greenfield couple 11 days ago. Family in Delaware. Yeah, so the situation is this, you know, how do you know when carbon monoxide is going to form? You know, normally when we burn, like say you have a stove or a heater or something, normally when you burn it, you should form CO2, right? CO2 in water. But sometimes, you know, under different conditions, you get different products. We know, you know, if you have a yellow flame, that's going to be giving you a lot of carbon dioxide. And that yellow flame is a result of it not having enough air in the flame. So it's a situation like this, you know, when you have thiosulfate is known as a reducing agent. You know, what is it going to go to? Is it going to go to sulfite, or is it going to go to sulfate, or is it going to go to sulfide? You know, what is it going to go to? I mean, so it depends. Depends on the reaction conditions and depends on how you react it. Normally, when we use the chart, you know, the chart, you make certain base assumptions. When you use a chart, you assume that you're dealing with 1 molar, 1 capital M solutions. The gases are at 1 atmosphere or 1 bar. And so those are pretty standard, but when you deviate from the temperature is 298 Kelvin, but when you deviate, like change the temperature, change the concentrations, change the gas pressures, you can get other things forming. And so this is the concept behind skeleton. Skeleton, we just tell you, like thiosulfate gets oxidized to sulfate. So you're told. You'd be told methane, rather than going to CO2, gets oxidized to carbon monoxide. You know, that's what had to happen in those houses. What had to happen in those houses was the methane was not completely combusted. And we have something like this. Well, is methane going to carbon monoxide on our chart? No, it's not on the chart. So we would use the half reaction method for that. So we did this. Do you recall what problem we did this exact thing? Where one species was on the chart, oxygen from air, and the other species was not on the chart. And we had to figure out what the half reaction was based on the skeleton method. Does anybody remember what that example was? It was around that time, around the time of glucose. Ethanol. Good. That gives me, glad somebody remembers that. It's good. Ethanol. Ethanol goes to normally when we oxidize ethanol, we expect it to go to CO2. But it didn't go to CO2. You know, this is like when you burn ethanol. When you burn ethanol, you hope you make CO2. You hope you don't make a whole bunch of carbon monoxide, because if you're burning ethanol, You don't want to be breathing in carbon monoxide, it's highly poisonous. But that ethanol didn't go to carbon monoxide, it didn't go to CO2, it went to what? Well, not, the acetate was the example from the book. For me, it went to HC2H3O2, which is called what? HC2H3O2 is called acetic acid. So if you forgot what I'm talking about, was this. This was the half reaction, which went to ethanol. And how did I know it went to vinegar? You know, normally if I'm going to oxidize ethanol is very flammable. It burns the CO2. But how did I know it didn't go to CO2? How did I know it went to vinegar? The taste, right? If it went to CO2, it would have been sparkling, like sparkling wine. But in this case, it went to vinegar. So the wine tasted like vinegar. So that told me that it didn't go all the way to CO2. It was just oxidized to acetic acid. So it was partially oxidized. So that's this type of thing. So for example, zinc. Zinc is in the redox chart. So we could easily get the half reaction. The half reaction of zinc goes to Zn2 plus 2 electrons. Done. Then this one, this antimony oxide, Sb2O5, goes to this weird ion here, SbO plus. You know, where did that come from? Well, somebody must have detected that. Somebody must have tried that and see what happens, because you don't know what's going to happen. This is a reducing agent. This is an oxidizing agent. So we don't know what we're going to reduce it to. Maybe to antimony metal, or maybe to this, or maybe to that. So somebody figured it out. Just like this. I figured this out here. And so one of the half reactions we can copy from the chart, the other we can't. It's like this one here. Is tin on the chart? Yes, tin is on the chart. On the chart we have tin goes to tin 2 plus 2 electrons. Right, that's on the chart. However, this is not on the chart. This is tin goes to this, H2SNO3. That is not on the chart. And so we would have to use a half reaction method here, that is balance all elements other than, we'd split it off. First we do tin to this. Is nitrate on the chart? Yes, nitrate's on the chart, right? But when you look at the chart, nitrate goes to NO on the chart. This is nitrate goes to NO2. So both of these are not on the chart. So we'd have to balance out both of these. So for example, the first one I'd split off, tin goes to this, and then balance it. The second one I'd split it off, nitrate goes to NO2, and then balance that. So this is a case where they just mixed it together and see what happens. Mix it together, see what happens. So they balance out, the nitrate goes to NO2, balance the nitrogens first. Actually, then they quadrupled it. So one nitrogen. Then balance out the oxygens, we need to add up water. Then balance out the hydrogens, then balance out the charge. And then they quadrupled it to get 4 electrons here, because they need 4 electrons here. Same thing with the tin. Balance the tins first. Balance the oxygen. 3 oxygens here, no oxygens here, add water. Balance out the hydrogen. 6 hydrogens now. 2 plus 4 gives us 6 hydrogens. Balance out the charge, 0, and then plus 4 minus 4 is 0. And then add them together. This is skeleton redox. That's what we're doing here. This one is on the chart. Tin 2 goes to tin is on the chart. Tin 2 plus 2 electrons goes to tin. So I already have one half reaction done. The second half reaction is not. Nickel 2 goes to NiO2. That's not on the chart. I'm going to have to use a skeleton method to figure it out. If I look at this one, is oxalate, you guys recognize this? C2O42 minus is oxalate. Is oxalate on the chart? No. How about permanganate? Is permanganate on the chart? Yes. And that on the chart it goes, permanganate goes to Mn2+. So we're set. We just copy that one off the chart. Permanganate goes to Mn2 plus. We can copy that one off the chart, and what does that look like? Well, it looks like this, actually. They doubled it. What it looks like is permanganate plus 8H plus 5 electrons goes to manganese 2 plus 4 waters, and then they doubled it to get 10 electrons because the oxalate needs 10 electrons. And so oxalate goes to CO2. Oxalate, what they're doing is oxalate, they're just burning it, basically, or oxidizing it. So it's not completely oxidized. So oxalate goes to CO2. Balance it. So the same thing. You know, oxalate goes to CO2. 2 carbons, 1 carbon, so double it. And 4 oxygens is balanced. Then balance out the charge. And they skip some steps, of course, here. 48. Actually, 48's chloride's on the chart, but not chloride goes to chlorines on the chart. Not chloride goes to what's this called? ClO3 minus. Chlorate. Good. Chloride goes to chlorate is not on the chart, so we'll have to figure that one out, you know. And so, what are we going to do? Well, let's get rid of these. Chloride goes to chlorate. How many waters do I have? 3 to which side? Left. Good. How many hydrogen ions do I add? 2. Well, if I have 3 waters, how many hydrogens are in 3 waters? 6. So I need to add 6 hydrogens to which side? Right side. And then I have minus, and then plus 6, that gives me plus 5, so I need how many electrons? I need 6 electrons. Bring it back down to minus. So the other half reaction is going to look like, oh, it's not there. I thought they answered it there. It's going to look like this. Chloride plus 3 waters. It's going to go to chlorate plus 6H plus. Okay, then we got the minus 1 on the left, so this is minus 1, so we need plus 6 electrons. So 6 positive, cancel out 6 negative, leaving us with 1 minus. This would be the balance. Half reaction there. The other half reaction we just copied off the chart. Nitrate goes to NO, so right off the chart. Nitrate plus 4H plus 3 electrons yields NO gas plus 2H2O. So that's right off the chart. And then we just balance it by multiplying the second one by 2 and then adding them up. What's this called? Dichromate. Is dichromate on the chart? That one here, dichromate. Yeah, it is on the chart. The dichromate goes to chromium 3 plus. Dichromate goes to chromium 3 plus is on the chart. Not that you have the chart memorized. It's just, you know, do you remember seeing it or you don't remember seeing it? That saves you a lot of time. In the long run, it saves you a lot of time because it means not having to go through the skeleton. If you can just copy it off the half reactions chart, we could save time. There are people who don't, and they end up going through it. Like nitrate goes to NO, they go through the whole steps to balance it, whereas they could have just copied it off the chart, save them a little bit of time. Not huge. But we have dichromate on the chart, but we can't use it. Why? We can't just copy it down. How come? because on the chart, do you recall what it is? It's dichromate goes to chromium 3 plus. Dichromate here goes to chromium 3 plus here. Whereas when we look at this is dichromate. Do you see chromium 3 over here? No. And so it goes to a different product. It's dichromate goes to Cr2O3. So we have incomplete reduction. It doesn't go all the way to chromium 3. It doesn't go all the way to chromium metal. It's like methane. Methane goes to carbon monoxide instead of carbon dioxide. It can happen under certain conditions. So under these particular conditions, the dichromate went to Cr2O3, which means that we'll have to balance it. And then ammonium. Have you seen ammonium on the chart? No. Ammonium's not on the chart, so we'll have to balance out. So in this particular case, neither of those are on the chart. So in order to figure out the half reactions, we'll have to split it up and balance them individually. So for example, dichromate goes to Cr2O3. We can do this pretty quick. Like after you do a bunch of these, it'll go pretty fast. 2 chromiums, about 7 oxygens, 3 oxygens. How many waters? Those 4 waters. 0 hydrogens, 8 hydrogens. How many H pluses? 8. Okay, plus 8 minus 2 is plus 6. 0 plus 0 is 0. And so I need to go plus 6 to 0. How many electrons do I need to add? 6. That's 6 negatives plus 6 positives gives us 0. That will be it. Then we look at the other one. The other one would be ammonium goes to nitrogen. Ammonium goes to nitrogen. 1 nitrogen, 2 nitrogens. How do I balance it? 2 ammoniums. No oxygens, so we skip that. 8 hydrogens, no hydrogens, so plus 8H plus. Plus 2 plus 8. We got to get them to match by adding negative charges. And so this has got to be plus 6, 8 positive, plus 8 minus 6 gives us plus 2. Plus 2 plus 2, it's balanced. And then that's 6 electrons. This is 8, or no, this is 6 electrons, so it just adds up, It adds up 1 to 1. You see what they did here? It adds up. How about this one? Sulfate goes to sulfur dioxide. Is that on the chart? Sulfate goes to sulfur dioxide. Do you remember seeing sulfate on the chart? Is that on the chart? Yes. Do you see it here? Sulfate goes to sulfur dioxide. So I'm just going to copy it. Just copy it right off the chart. Mercury goes to mercury 2. Is that on the chart? Mercury goes to mercury 2. Is not on the chart. So we'll have to balance them. It's easy to balance them. AS2O3 goes to ASO4 3 minus. Is that on the chart? No. nitrate goes to NO, is that on the chart? Yes. Pb2 plus goes to PbO2, is that on the chart? No. Zn2 plus goes to Zn, is that on the chart? Yes. And so we have the chart method, and then we have this this hybrid method where it's a combination of chart and skeleton. And then we have pure skeleton, which, you know, the species don't appear on the chart, so we have to do skeleton for both. Then we got combustion reactions. Single replacement. What did I say about single replacement? There are exceptions. I assume nobody's memorized the exceptions, right? Last time I checked, nobody had them memorized. And so stay away from single replacement. Instead of single replacement, use the chart method, right? Or you got to get the right inventory. All right. We're going to continue with this. The exam is going to start with redox, and it's going to end with Lewis structures. The sample test I had online includes all of chapter 13. We're not going to do all of chapter 13. We're just going to do Lewis structures. Okay, so the shape stuff you don't have to worry about. So we left off with C2H6O, correct? We got C3H8O2. Is that right? For organics, we can do them a little differently, you know. What we do is like C3H8. So C3, we just make a 3-carbon chain, like that. We have an O2. Let's see, let's make the H's like this. H5, then maybe we'll stick an O here. 6, and maybe another O7, and hydrogen like this. And complete the octets. As long as there's no formal charges, then we have the right number of valence. I mean, carbon's supposed to have 4 valence. It has 4 valence. Hydrogen has 1 valence. Everybody breaks even here. All the formal charges are 0, so the number of valence electrons that contributed is the same as the structure. This is how we do it in organic chemistry. In organic chemistry, we don't sit there and total the number of valence because we could see the number of valence just by looking at the structure. I see that everybody has the correct number of valence electrons, everybody has an octet, and therefore it's good. However, you know, what did I talk about the other day? The same formula but different structure. What's that called? Isomers. And so there are a lot of isomers for this. And so, you know, one isomer is where you put both of them on this last carbon. Or I move this OH. I can move this OH to this middle carbon. Or I could move this OH to the end carbon, so I have OHs on both ends. So there are a whole bunch of isomers that are possible. And so this is just one isomer. This one's called ethanol here. It's a 2-carbon alcohol, ethanol. This one is called 1,3-propane diol. So there's 2 alcohol groups on it. Just the other day I got this one, 1,2,3-propane triol. This This is 1,2,3 propane triol. One, two, three, propane triol. One, two, three, propane triol. Let me buy this stuff. This is a very important molecule in biology. Do you know it goes by another name? Do you know what the other name is for it? It's called glycerin. Glycerin, or glycerol, is product from fats. Usually when you have fatty acid part attaches to this, and we create a fat molecule. A fat molecule would have this, when you start to digest fat, the glycerin or glycerol molecule. It's also called 1,2,3 propane triol. 1,2,3 propane triol, i.e. glycerin or glycerin. This would be 1,3 propane diol, di meaning two alcohol. But we could have 1,2 propane diol as well. You know, the numbers come from numbering the carbon atoms. Here, you might think this is a 2,3 propane diol, but it's not a 2,3. This is a 1,2. We number it so that it comes out the lowest number, not the highest. So if I started the chain here, 1, 2, 3, then it would be 2, 3, which would be the same thing as 1, 2. So let's go with 1, 2. C6H14. C6 is hex. Now hex, 6 carbon chain. 1, 2, 3, 4, 5, 6. 6 carbon chain. And let's just fill them with hydrogens here. So how many hydrogens do we end up with here? So we got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is called hexane. Hexane. Hexane is actually a liquid. You know, propane's like almost a gas, liquid gas, and at the quarter. Butane's a liquid. Ethane's a gas. Methane's a gas. But hexane's a liquid. C4H6O. So for organics, we do it a little differently. I'm going to figure it out. You know, I don't know, is that an ether or is that an alcohol or what is that? You know, so we can come up with different structures. And those different structures are called isomers. Let's do this one. Let's do butanoic acid. Butanoic acid. It's that COOH group there. COOH group. Do this here. Move that over here. So butanoic acid is C3. So what we're going to have is but is 4 carbon chain. So we're going to do it like this. It's just this 4th carbon is the COOH group. The COOH group looks like this. Organic chemists would know automatically that that's the structure you draw for that. This is the carboxyl group. And then the rest you just fill in with hydrogens. Here, we're going to fill it in with hydrogens. There's no double bonds here other than the one to oxygen over there. So this would be the C3H7, 3 carbons, and 3, 4, 5, 6, 7 hydrogens. This is called a propyl or M-propyl group attached to it, but it's but because we have 4 carbons. So this is butanoic acid. Butanoic acid has a very bad smell to it. There's some butanoic acid in your stomach. If you vomit, then smell or taste of butanoic acid. acetic acid also has a bad smell. Let's look at some of these others. Acetic acid I drew the Lewis structure for. Let's take a look at NO2 plus and N2O. Now, for organic we kind of do it this way because we know the building blocks for that. But when we go to inorganic, for inorganic we don't do it this way. We do it back to the traditional method. So NO2 plus, we got nitrogen with 5 electrons, 2 oxygens with 6 each, so that gives us 12 electrons total, a plus 1 charge, which means take away 1 electron. So NO2 plus is going to have 16 electrons. So how should we do this? Well, we have 2 choices. We could go NOO, but I don't like this. Why? Automatically I don't like this because this oxygen-oxygen link, the peroxide style bond. I don't like that. So it's probably better to go ONO. It's not always going to be like that, but we'll do it like that. We're going to go ONO for this. And then let's complete the octet. Who gets first, oxygen or nitrogen?
Oxygen.
Because, yeah, it's more likely. Okay, and then, can you count how many electrons? I already see how many electrons I have. How many electrons do I have? I have 16 electrons. I'm only allowed 16, so I can't complete nitrogen's octet. The only way to complete nitrogen's octet is by to form a double bond. So let's go ahead and we'll just take this pair here. We'll make 2 double bonds. So it's going to go O and O, like this. Now, does everybody have an octet? Yeah, it's good. And then we need to do what? Is the final step? Formal charge. Tell me the formal charges. 0, plus 1, and 0. Well, this whole thing is an ion. It's a positive ion. The NO2 plus. N2O. N2O is called dinitrogen monoxide. It also has another name. We aren't going to name this. Is this called nitrogen dioxide? No. It's an ion. It's called nitrosyl ion. I think this is nitrosyl. That's the name of this one. And that's one of those common names. Like it's one of those ones that you just have to memorize out loud. So nitrosyl, I think as I recall, is NO plus. So NO2 plus. NO2 plus ion is called NO2 plus. It's not nitrite. NO2 minus is nitrite. NO2 plus is called nitronium. That's 2 double bonds. You can see like that. Nitronium ion. N2O is dinitrogen monoxide, aka what? 2O. Give me another name for N2O. You probably know it. Yeah. Nitrous oxide, also known as, you know what nitrous oxide is known as? Laughing gas. Nitrous oxide is laughing gas. Oops, I didn't want to show you that structure. Ignore that structure right there. So, how do we want to do this? Well, I'd like to do it like this, N-O-N. Does that sound good? N-O-N. The oxygen likes to bridge things, like for example, H-O-H. H-O-H is called H2O, which is called water. Or COH. You've seen COH, like carbon, oxygen, hydrogen. What's that called? That's called an alcohol. NON sounds reasonable, doesn't it?
Least electromagnetic have to
I'm sorry?
be. Doesn't the least electromagnetic have to be?
Yeah, right. I'm violating one of my rules. One of my rules is the least electronegative element should go in the middle, but you know, oxygen is plenty happy. Like here, HOH. No, it's not the least electronegative. Or how about this one? COH. So oxygen can go in the center. Maybe it's okay here. No, like in the alcohols. And so let's just try this. NON. And try it. 2 nitrogens, how many electrons? 5 times 2 is 10 oxygen. So I have 16 electrons. Let's complete the octet. And that takes care of how many electrons do I have now? Octet is 8, so I have an octet here, 8, octet here, 8. 8 plus 8 is 16. That's 16 electrons. Is this a good structure? No. The oxygen doesn't have an octet. In fact, I probably should have filled the oxygen's octet before nitrogen, shouldn't I? Because oxygen's more electronegative, but that's okay. What we're going to do is we're going to just do multiple bonds, just like we did in the previous example. Now everybody's happy, correct? Everybody's happy because everybody has an octet, right? Well, there's one more step, step 6, which is not in the book, but what is our last step? Formal charge. So let's take a look at the formal charges. What are the formal charges here? Nitrogen is minus, oxygen is plus 2, and nitrogen is minus. And so essentially, in this structure, oxygen was robbed of 2 electrons by nitrogen. That's what redox is. Nitrogen is going to take the electrons, I guess, from the oxygen. That seems. But does that make sense? Because which one's more powerful, oxygen or nitrogen? Oxygen. And so for oxygen to lose 2 electrons is significant. And so it has me worried about this particular structure. Well, what if I triple bond it? Let's go with triple bonds on both sides. Now what are the formal charges? 0, 0, 0. So problem solved, right? With triple bond, then problem solved. Right or wrong? Wrong. Wrong because, yeah, oxygen. Oxygen, can oxygen have more than an octet? No, it's second shell. Like, this is impossible. Oxygen cannot exceed an octet. Oxygen cannot exceed an octet. So we're stuck. We're stuck with this structure. Oxygen contributed 6 electrons to this and only got 4 back. It's not going to be happy. If it contributed 6 and only got 4 back, it's not going to be happy. Nitrogen only contributed 5 each. Nitrogen only contributed 5 each, and they came out ahead. They got 6. Let's try following the general rule. The general rule is in the center goes the least electronegative. So if we put the least electronegative in the center, then this is a skeleton we get, an NNO skeleton. And then let's complete the octets. Let's do oxygen first because oxygen is the most electronegative. Then we'll do nitrogen. And that takes care of 16 electrons. Now we have a choice. Choice 1, nitrogen sacrifices. And okay, so if we go choice 1, nitrogen sacrifices, we'll make a double bond here. still not there yet. We're still not there yet because, why? It doesn't have an octet. And so, well, okay, nitrogen made that sacrifice. Now what we're going to do is we're going to make oxygen make a sacrifice like this. We'll call that A. And so both nitrogen and oxygen will make a sacrifice to complete the octet in the center. Now, does everybody have an octet? Okay, what are the formal charges? Nitrogen is negative, this nitrogen is plus, and this oxygen is 0. Okay. Maybe let's go with a triple. We go with a triple here. Actually, I'm going to get rid of the formal charge entirely. So what I'll do is we'll go triple here. Go triple here, and then double. Then what are the formal charges here? 0, 0, and 0. 0, 0, 0. That's great. If we can minimize the formal charge, that's great. And so sometimes we like to minimize the formal charge by doing this. What is this called? By expanding it. It's octet. Well, whose octet did we expand? This nitrogen, the central nitrogen, now is 2, 4, 6, 8, 10. Can we expand the octet on nitrogen? No. So even though this is great, we cannot expand the octet. We cannot expand octet on nitrogen. And so we're stuck with that one. But you know, this is fair, right? Nitrogen sacrifices, oxygen sacrifices. But what if it wasn't fair? Let's say instead of having this, what if we did this? We end up at the same spot here, but rather than having oxygen sacrifice, let's have nitrogen sacrifice again. We'll call that B. And so what we end up with is a nitrogen triple bond here, but a nitrogen oxygen single bond here. Does everybody have an octet? Yeah, everybody has an octet. What are the formal charges? Okay, this nitrogen is, and this oxygen is minus. So the central nitrogen is going to be plus no matter what. We can't expand the octet to get rid of that. And so the choice is this. Who gets the extra electron? Nitrogen in the top structure or oxygen in the bottom structure? Which one do you think is more favorable? Nitrogen or oxygen getting it? Oxygen. Why? More electronegative. More electronegative. So here, let's take how much more electronegative though. Yeah, oxygen is more electronegative than nitrogen, but is it hugely more? The 3,4 versus the 3,0. And so what we have are, these are what we call inequivalent resonance forms. This one is going to be a little more favored than this one. You know, this one is more stable because oxygen has it. But nitrogen is not totally weak. This is versus equivalent resonance forms. Equivalent resonance forms would be something like carbonate. This is one. There are 3 resonance forms for carbonate. Did we do carbonate yesterday? No? When you do carbonate, you come up with 3 resonance forms, depending on where you make the double bond. We did? 2 days ago. I'll write it again. And so this is 2 minus, 2 minus, 2 minus. And so these are all equal in terms of energy. These are called equivalent resonance forms. These are not equal here because and this one's a little more stable because oxygen is 3,4, nitrogen is 3,0. You know, so be a difference. But as far as the best structure goes, which one is the best structure? This one is the best structure. And so if you're going to write the best structure for this, it would be this. For carbonate, which one of these is the best? They're all the same. N2O. So N2O, let's see what structure they have for N2O. Which I try to hide. You see? N2O is nitrogen-nitrogen triple and a nitrogen-oxygen single. That's the best. Nitrous oxide. Of course, you have different possibilities, as they're showing the different possibilities. This one's quite bad. Do you think oxygen's going to sacrifice and nitrogen doesn't have to sacrifice at all? I didn't even draw this one up there because, you know, if somebody's going to sacrifice oxygen versus nitrogen, it's going to be nitrogen. It's less electronegative. Didn't even bother. That would have been another choice up here, but I didn't bother with that choice. But, you know, on the test, they see all kinds of structures. NO plus. Let's do that. Next. So again, handle inorganics, going to figure it out. Nitrogen's 5 electrons, oxygen's 6 electrons, plus 1 is minus 1 electron. 10 electrons. So this is easy. It's got to be nitrogen bonded to oxygen. Who we're going to complete the octet to first? Nitrogen or oxygen? Okay, that takes care of 2, 4, 6, 8, 9, 10. But somebody doesn't have an octet, and how can we do that? We can form multiple bonds. If I take this pair from nitrogen, it doesn't change anything. I gotta take it from oxygen. And so I'm gonna have to form a double or a triple. I need two more pairs, so I'm gonna have to form a triple. What are the formal charges? Nitrogen is, oxygen is plus. You know, on the one hand, you know, if the plus charge is going to go on something, it should go on nitrogen. We can make nitrogen have a plus and oxygen be 0 by going back to this. If we go back to this, what is it? Nitrogen is plus, and oxygen is 0. But the problem with this structure is what? There's a problem with this structure. Nitrogen doesn't have an octet. And so in this particular case, yeah, oxygen doesn't want to be the loser, but it's going to have to be the loser in order to get an octet. Where did we see that before? No, fluorine's not going to lose no matter what. BF3, fluorine doesn't lose. There's another molecule in which oxygen lost to carbon. Which one was that? Oxygen lost to carbon. But we had to do it to get an octet. Which molecule was that? You have it in your notes? You know, you write in little reminders in your notes, you know, what was the point of this, or what was the key take-home message of this? Well, the key take-home message of that molecule is that it was unusual. Oxygen had to make a sacrifice to carbon in order to achieve an octet. What molecule was that? Not HCO3. What did you have? No, not carbon dioxide. Not HCO3, not carbon dioxide. It's because of that structure which makes it an exceptionally poisonous molecule. It was the same time I was talking about BF3. It was right after I talked about BF3. So right after I talked about BF3, what did I talk about? Carbon monoxide. Carbon monoxide is exceptionally poisonous because of that negative charge on the carbon. Oxygen made that sacrifice, I guess you can say, to get the octet around carbon. But you know, when we see something like this, carbon monoxide, we can see that this is like cyanide. If you look at cyanide, cyanide's like this. What's the formal charge on carbon in cyanide? Minus. What's the charge on nitrogen? 0. Cyanide and carbon monoxide are similar. Both are highly poisonous. Both attach to hemoglobin and don't break off. What attaches? That carbon attaches. Why? The carbon, having that negative charge there makes it what we call an exceptionally strong Lewis base. And the reaction between carbon monoxide and cyanide and hemoglobin is a Lewis acid-based reaction. It's because of this. So both of these act in the same way, cyanide and carbon monoxide. And so it's like, it's like when you're generating carbon monoxide, you're generating like cyanide. You're breathing cyanide. Do you want to breathe cyanide? No. They used to, in California, they used to have a gas chamber. So you use cyanide gas, hydrogen cyanide gas. So in this case, in this case, the nitrogen is 0, but this carbon is actually positive, so this is kind of weird. Cyanide's an ion, carbon monoxide is neutral. But they have both the same kind of action because of this carbon. It's the carbon. It's called a carbanion. Carbanion. They have carbocations and carbanions. 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 It's a carbon with a lone pair. But people don't call them carbanions. Carbanions. Yeah. Okay, let's continue here, but we'll take a break and then we'll continue after the break.